Okay, so today we will finish the part of special relativity, and then we will start relativistic quantum mechanics. Now, Tuesday we got to the full Lorentz group, and we said that the algebra of the generator, the Lorentz group, include the rotation in 3 dimensions and the boost. The boost, it means the change of frame by a velocity in 3 dimensions. And the generator had the following algebra: J, 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 I, epsilon, I, J, K, J, K. These are the generator of rotation. The generator of boost were called Ka, Kj, and their algebra is we did not derive this, but of course it is possible to derive from the manner the okay, so this is the full Lorentz algebra. These are the generator of the boost and the K, and the J, the generator of rotation. As in analogy with the rotation group, where out of the rotation group you built a Casimir that is a J squared that commute with everybody, and you diagonalize that, we find out that there are 2 operators defined in this manner that commute with all 6 generators. I put an arrow to indicate that there are 3. This I goes from 1 to 3. And then there is a second one that is defined J times K. Okay, so basically this commute with all the 6 generators. You can diagonalize them, get their eigenvalue, and their eigenvalue will characterize the representation. We will not go into this detail anyhow, just an indication of how things go. But last things we did we introduced 2 new. Instead of these 6 that have this strange algebra, we somehow tried to decouple the algebra to see if there were some combination so that the 2 algebra of new operator get decoupled. And in fact there is, if you introduce these 3 operators defined in this manner, and B 1/2 J minus AK, then it's easy to see that each of them has the algebra of the angular momentum, and that A and B J commute. So when I say decoupled, it means this, and the 2 algebra are 2 algebra of the angular momentum. So you think you can proceed as with the angular momentum. That is not so, because look there, the A dagger is equal to B, so they are not Hermitian. If they are not Hermitian, you cannot apply all the things of the angular momentum. I told you, go and look at when you apply the things of the angular momentum, you build the A square and then diagonalize the A square and so on and go on, and build the representation, and it can be an integer or half integer and so on and so forth. But a crucial ingredient was the hermeticity of the thing. This is not Hermitian. They are not Hermitian, so you cannot apply that technique. And in fact, what is possible to prove is that the number of, when you diagonalize A square, and for example, you get a number like, remember 1/2 plus 1, and this is 3/4, and there are 2 states associated to that. Well, that is not the case anymore. What happens is that you have that if you insist on having unitary representation, you have that they are not finite anymore. So one statement that can be proved, I just stated, but that the unitary representation of the Lorentz group are not finite dimensional. So that is one of the things that you lose because of this lack of hermeticity among the operator. And now you can say, oh, but we built the J and the K as 4x4 matrix as an example Tuesday, and those were finite dimensional. Remember that we built the Jx, the J, and it basically was 1, and here the generator of rotation, let's call Lx. Okay, the Jy, this is 4x4, the Jy is 1, and the generator of rotation Ly, and the Jz as 1, Lz. Okay, and we built the Kx. They were in this manner: 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. The Ky was 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. And Kz as 0, 0, 0, 1, 1, 0, 0, 0, all the rest 0. And they were finite dimensional. So what's the matter with that statement? Well, if you remember how the generator were built, the rotation generator were exponential I, an angle alpha, a unit vector times n, and these were Hermitian, so this is unitary. Okay, but now if you build the L, if you remember the L, because there was that cosine hyperbolic for the Lorentz transformation, the things was E, V, a unit vector, V, the modulus of the velocity, a unit vector in some direction, M, times K. And you notice that there is no I here. So even if K is Hermitian, this is not unitary. So this is a non-unitary representation of the Lorentz group. Okay? We will be interested in the unitary one, so we will build infinite dimensional. And the infinite dimensional, we will not enter this fine mathematical detail, but are associated with the Klein-Gordon equation and the Dirac equation and so on and so forth. So I have given only some qualitative things. Then each of you, if is interested, whenever you have time, you can go and just study more, but it's not required by the program of the course. Okay, I just give for your own culture because I imagine that many of you already knew special relativity, so I thought that I would give a little bit of this Lorentz group. So the Lorentz group is a group that has 6 generators, 2 Casimir, rank 2, but it can be decoupled into 2 apparently harmonic oscillator angular momentum, but we know that one, the rotation, is a real angular momentum, the other is not, and these operators are not Hermitian, so basically the unitary representation of the Lorentz group are not finite dimensional, and you see, because you cannot use the hermeticity, and then you cannot really work as in the rotation group. Please? Is it correct? KX? 1. Okay. Okay. Now let's go on. And before going on, we will, as I told you, we are following now a standard textbook, and we will use the notation of the standard book now. So I have to review a little bit I have to introduce to you, which is the notation, is one of the many that we have jumped from here to there, and I prefer in the special relativity review give you all the possible convention. I never specify to one or the other, so just because I was taking from different books and because I wanted you to know. Now, let's first of all introduce the concept of, well, let's go do one step at a time. We knew that the invariant under Lorentz transformation, that this quantity written here is an invariant quantity, does not change under any Lorentz transformation. And is a sort of 4 length with this. This is somehow the analog, the relativistic analog of the things that is invariant under rotation. Okay. Now, and these objects are the component. This can happen for many vectors. That means you can have an object with 4 index mu, an A0, A1, A2, and A3, and you call these, now you ask yourself, how does it change under a Lorentz transformation? So let's indicate the Lorentz transformation with a matrix. If this object, the new object in the new frame, transform it, this is the Lorentz transformation. It is a matrix, so it has 2 index. If it transforms in this manner, okay, then you call this object with the index up, I always mix up the things, controvariant. So this is a 4 vector, and if it transforms under a Lorentz transformation in this manner, this is called controvariant 4 vector. Basically, the controvariant one, we put the index up. Okay. Now let's take out of this controvariant the analog of that. That means the analog of its length, but pseudo length. Then it will be A0 square minus A1 square minus A2 square minus A3 square. And if this is a 4 vector, then we know that is invariant, that is length, like the length in 3 dimensions. If this is a 4 vector, its length in 4 dimensions is invariant under, so its length defined in this manner is invariant under a Lorentz transformation. Okay. Now, this quantity, this 4 vector, instead of every time having to remember 1 plus and 3 minus, we introduce a new notation that is the one of covariant vector. That is object that have the index down, and the index is brought down in this manner. You introduce a metric G mu nu and nu. So you take a controvariant vector multiplied by a strange matrix that is called metric. So if you want, this is the definition. This is a definition of covariant 4 vector. So covariant 4 vector is defined in this manner. You take an object that is the metric, that now I will tell you what it is, and multiply by the controvariant vector, and that, you know, is an object that transforms under Lorentz transformation in this manner. Okay? Now, what is this metric? We have already talk about it. This metric G mu nu is a metric that has the following form. Let me use the notation of the book so that I don't do mistakes. Okay, is 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1. Okay, so this is the 4 metric, and now you see this object can be written, this, that is the 4 vector, can be written in a very compact way as the following: G mu nu a mu a nu. Okay? Because basically this is 1 minus 1 minus 1, so you have a0 square minus a1 square minus a2 square minus a3 square. When the index are crossed, it means the Einstein convention, they are summed. Okay? But this object can also be written in another manner. This is the definition of the covariant component. So this object can be written as a nu. So this one is a nu, and this one is a nu. So this object can also be written in this manner, a nu, because we have defined the covariant component. So the contravariant component of a 4 vector have the index up. They transform under Lorentz transformation in this manner. The covariant one have an index down, and they are defined in this manner. Okay? Now, why I put the index down or the index up and so on and so forth? Because I have the convention that if one index is up and the same index is down, the Einstein convention says they are summed. So here, the Einstein convention tells me that ni is summed, while mu is not summed, and in fact it remains a free index here. So this is the contravariant, this is the covariant. The 4 length, you can either write with the metric, that is the object that transforms the covariant into contravariant, but you can, as these objects, so you can write in this manner. But this object, this first part, this is the contravariant, can be written by the definition as the covariant multiplied by the contravariant. The index is 1 up and 1 down, it means they are summed, so you can write in this manner. Now, if you do this explicitly, you get this expression that is the 4 length of the 4 vector a mu. Okay? Now this is the nomenclature that we will keep. The last things that we will do about this is, if the contravariant vector transform by definition, so this is a definition, if this is the Lorentz transformation, the generic Lorentz transformation represented that either as one of those 4x4 matrix, but it will be no unitary, or by an infinite dimensional matrix. If this is the manner contravariant vector transform, can we derive a covariant vector transform under Lorentz? So this is the next question that we will answer. Is there any question here? Because the blackboard is small and I have to cancel. You find all these you find all these in the book that I gave the reference to you, Relativistic Quantum Mechanics, and I'm just really following the book and not adding anything so that you don't get confused also. Okay, let's see. Yes?
Is it just a name when we say covariant vector?
Yeah, it's just that's a name like Ennio or John or whatever. Okay. No, there is not physical meaning at this level. There is not physical meaning. It's just definition. The general concept of covariant is much more general, but not in this sense. Covariant, it means basically that an equation of motion keeps the same form when you go into another frame. But that is another meaning of covariant that we will not touch. For the moment, just keep this meaning, okay? Because otherwise it's easy to do confusion. Okay, so let's leave this and let me, okay. Let me rewrite part of this in a smaller way. Okay, so we have seen that the 4 vector, so A0 square minus A1 square minus E2 square minus E3 square, this one can be written as mu, and this is the same as A prime mu. So, and it can also, if you want to, okay, forget about this. So this is the 4 vector. It can be written in this manner, or it can be written in this manner: G mu nu, A nu, okay? So I bring down the index with the metric, or now what I want to know is the question that we will try to answer is the following: if A mu, the contravariant one, under a Lorentz transformation, transform like that, where these represent the Lorentz transformation, then all the covariant one, the one with the index up, and with the index down, will transform. Which is the matrix that I have to put here? You might think it's the Lorentz. No, it is not, because you see, you look here, this object is invariant, okay? We know that this one transforms with the A lambda. So the other will transform with the inverse in order to preserve this distance. So basically, A mu is equal A nu lambda to the minus 1 mu. Okay? Why it is so? You look at here. You know that the one with the index down transforms in this manner. Okay? So if you insert the transformation, you get then the A mu transform in this manner, okay? Let's do it explicitly if you have not understood. Let's start from here. We know that this 4 length is the same. Then we have A mu equal A mu prime. And this object, we look, this object there is lambda mu A nu, and is this object, then A prime mu. Then remember that this is a matrix with these 2 indexes. So from here, you can immediately derive that A mu, now multiply by the inverse of this matrix on both sides. But you see, there is an index that this index is saturated, these 2 indexes is saturated, these 2 indexes is saturated. It's immediate that if you multiply by lambda to the minus 1, what you get is A prime mu is equal A nu lambda to the minus 1 mu. Okay? You understand what I've done? The length is left invariant. So I replace this part, because I know how it transformed, the one with the index up, in this manner, and I get this relation. Okay, from this relation, I leave as an homework to you, because it's very simple. This is matrix multiplication. You get that the A mu prime must transform in this manner. So here we have answered the question. The A mu prime is A nu lambda to the minus 1 mu. Well, we can write this object using the metric, if you like, we can write this object like as G mu rho a prime rho, okay? And we know this is G mu rho. We know how this transforms. It transforms in this manner. So this is equal to lambda, so G mu rho. Now we know how this transforms. It transforms in this manner, rho sigma, a sigma. I have transformed this in this manner, okay? And now what I can do, I can bring this down, G mu rho, lambda rho sigma, and then I bring this index up like G sigma ni a ni. And now you see I have introduced a metric that has both index up. I will come in a moment, okay, how to define this object. This object with the index, both index up, that is a metric, satisfy the following, is defined in the following manner. G mu nu, G nu sigma is equal delta mu sigma, where this is the identity. So this is the definition, if you want, of this object that is the metric with both index up. Okay, but now let's look at this relation. If we look at this relation, we see immediately that this relation implies the following. It implies that, just a moment. Let's see how we can do. Now, this is the transformation. Okay, we have derived this. Now, well, let me write down the relation I want to get. A prime mu is equal G mu rho delta rho sigma G sigma nu nu. Okay, and you can see it from here. This object is nothing else than this with the index down, and this object is this, okay? Now look these strange things, but we know what these strange things must be because we have already derived here. So it tells you that this quantity must be equal to this. That means from here you derive the following relation, that delta to the minus 1 nu mu is equal to G mu rho lambda rho sigma G sigma nu. Okay? Let's call this object from now on. You see, this object, what happened? It is a matrix on which these G act, but the G only raise and lower indices according to that convention. So this is nothing else than a lambda in which we raised and lowered sigma and mu, so basically mu, nu. Note that this is different from this, not the position of the two indices, okay? So this is the relation satisfied by the Lorentz transformation and its inverse. You take the inverse and take then the matrix element ni mu is the same as the same matrix with the index mu and nu, and that the index mu and nu, one is down and one is up, you see from here, okay? Now this somehow is analog of the fact, you know, here having moved the index, it means like the transposed. So it's something like the inverse is equal to the transform. So somehow it is analog to the unitarity relation, but only analog. So this is a property satisfied by the Lorentz metric. Okay, we will not use so much this kind of thing, but it's important that once we do. So I just go through it again so that we define the contravariant vector as vector with the index up, and the transform under a Lorentz transformation, where the Lorentz transformation is one of those that we have seen before in this manner. Okay. Then we introduce a metric that basically the role of this object is to bring the index down. So we define an object that is called covariant with the index down, built in this manner. So this is just a definition. There is nothing, and the metric is defined, I can say before, G mu nu with the index down is defined as 1, 0, 1, minus 1, minus 1, minus 1, and all the rest 0. Okay, so this is just a definition. Please.
Which quantity, physical quantities can be described by this?
This basically you see from here is the object that is needed to get the 4 length. You see? So the metric is always associated to a 4 length, but is also associated to the lowering and raising index. This, remember, was the 4 length. It can be written in this manner, okay? This object, because of the definition of the metric, we can write it here. G mu nu nu is these things. So you see, it's always associated. The metric is always is always associated with a 4 length, but as definition, we use this. This is just a mathematical definition. And then we do the 4 length, and we see that it enters. So a metric is always associated to a 4 length. That means if I give you a metric, you know the 4 length of some vector. That is this. Okay? And the metric, this is what they call a flat metric, in the sense that it does not depend on x. It is the same everywhere. You will see when you do general relativity that the metric can change from point to point, okay? So the metric is always needed when you want to have a 4 length defined. Then the next question that we ask ourselves is the contravariant vector transform in this manner under a Lorentz transformation. How the covariant one transform? Okay, so this is the question we wanted to answer. Sorry, no, this is what is the definition somehow of the question we want to answer is this: how does it transform? And the result we got, I don't go through the step again, is that the covariant component of a vector, the one with index down, transform in a manner that is the inverse of the one that the covariant, the contravariant one transforms. So the covariant component of a vector transforms in a manner that is the inverse of the one with which the contravariant one transforms. And the proof is here, okay? Or the proof is the fact that the 4 length is left invariant by a Lorentz transformation. Then if a 4 length is left invariant by the Lorentz transformation and you write the 4 length in this manner, then it's easy to derive these things, okay? And one can go and see that these, because of the invariance of the length, that this object can be written also in this manner, where you introduce a metric with the index up that basically raises the index and is defined in this manner, okay? You will find all this in the first few pages of the relativistic things, okay? So just for the main concept, we need a metric to lower indices, okay? And the lowering of indices is just a definition. So with the index sub we call contravariant, and it transforms under Lorentz in this manner. So somehow this is the definition of contravariant. It doesn't matter where I put the index. If you have a 4 object, an object with 4 components, that under Lorentz transform in this manner, with this is the real Lorentz transformation you are implementing, then you call that vector contravariant. As a convention, we use the convention that the index is up, okay? So contravariant, if I ask you in the final exam, what does it mean contravariant? Don't tell me it is something with the index up. No, I mean, it doesn't matter, it's a convention. A controvariant is an object that transforms under a Lorentz transformation, where this is the Lorentz transformation, in this manner. Okay? Then, next, you can define, introducing the metric, an object with the index down, and then you can ask the question, this other object, how does it transform? Well, we found that this other object that we call covariant transforms with the inverse matrix. Okay? So controvariant is an object with 4 components that under Lorentz transform in this manner. This is the definition of controvariant, where this is the direct Lorentz transformation. You then define, this is a definition, covariant 1, and by convention we put the index down, we define it through a metric, and then we ask ourselves, if this transform in this manner, how this transform? The covariant, the one with index down, transform in this manner, and here is the derivation. It doesn't matter if you have not followed the detail. It's important the result. I will never ask you the detail. It transforms with the inverse matrix, but note, the inverse matrix now is applied on the right, so basically it is the transpose of the inverse matrix, okay? You see these act here in front, and these act, so basically these are like row and these are like column, and that is so, you can see from here, you know, you get a number multiplying these 4 objects with these 4 objects, so it's like multiplication by row by column, okay? And then if this is a column and not a row, it has to transform with the matrix on the other side, but which matrix? The inverse. Why? Because the length is conserved. Okay, I don't want to repeat it again. You find all these in the lecture I sent already the other time, last time. And okay, now that we know all, that we have all these, let's see and specify. Yes.
Now, if our Lorentz inverse transform acts on the right,
Yes, like here.
is it right to say that our contravariants?
Yes.
How we find the inverse of our Lorentz?
The inverse is like the inverse of a normal matrix, so that means you have the definition from algebra of the inverse, okay? But then you don't multiply it, you take that matrix, you don't take it and multiply in front of the vector. You don't multiply this lambda to the -1 in front of the vector. What you do this. You understand? So these things, it means take the inverse of the matrix, and that is an inverse and is a set of numbers. This object is this. So that means, you know, you do this multiplication like if this was a row. You understand? So this means the following. Is it clear?
Now, if we compare the two relations, because we want to find again the inverse of our Lorentz transform.
Okay, no. I found a relation now between the inverse and the direct one, and the relation is this, okay? Now, how I do? This object I write in this manner using the metric, okay? This object, okay, then I go home and I use this, and this one is transformed like the Lorentz, because this I know how it is transformed. Is a prime, is the index up, and I know is a contravariant vector, so it is transformed in this manner, okay? And so on, and then I go home, and you know, you have G rho. Now, this object I write as this manner, and so on. You understand? And then from here, now you can have, you get this relation. Huh?
We use that one and the previous one to find the
Now, this one, you agree that is nothing else than this. Okay. We have got that relation, so we put it here. Okay? But now, these and these are the manner in which this object is transformed. So all these must be lambda to the minus 1.
Yeah, that's what I'm saying. Is it rigorous to say it is exactly the same? Because here our operator acts this one
Yes.
on the left, but in the previous one it has on the right.
Yeah, oh, but it depends just how you put the index. You know, these objects act on these, and you are saying here instead it acts on the other side, but it depends only how I put the index.
Now from that relation, okay, the first relation, the index are the same for
But you see, this object has the index mu, nu. This object has the index mu, nu. While these objects has first the index nu and second the index mu. So the first index is the one that you go and sum. These two are not one above the other. Okay? It's like this. It's like this. Look which index you sum. You sum over the index mu. So the convention is that you have to put in this matrix, and this up, closer the index that you sum. Okay? And so basically this relation is the same as this, because this object has an index mu and an index mu and an index nu, but is sum over the index nu. So I write this object, the first index is always the one, the index that is closer to the matrix is the one that you go and sum. Okay? Maybe that is the convention that you are not familiar with, but I don't know, you did algebra. I mean, usually this is something that is known. You understand? So basically, the index that is sum is mu, is nu. Okay? So I have to put this index, if this object I put like here on the left, then I have to put this object closer to the vector, because it means this goes and sum it. If I put the vector on this side, okay? Go through it a little bit, because it is a good gymnastic and it tells you which is, even if we will not use much in detail except for the, we will use a little bit in detail when we do the Dirac equation, but there, if you have not understood, we will redo it again, okay? So, don't worry. Now let's go and see the convention that we will use for x, y, and z. This is the general things for 4 vector. Now, so let's now specify all these notations. So the contravariant one is this vector, and then the covariant one is g mu nu x nu, and then you get ct minus x minus y minus z. Okay, so the usual vector that we have used, often is the one with the index down, or the covariant one. Then x mu, this is really sum x mu, and is x0 plus x1 plus x2 plus x3, and then this object, this quantity ct square. Then one is plus and one is minus, so I get minus x2 minus y2 minus z2. Okay, so you see that these summing using the Einstein convention, some index that are repeated are summed, and this is also equal to g mu nu x mu x nu, is the usual 4 length. Now let's also go and introduce the analog of the momentum. P mu is E over C in our convention, Px, Py, Pz, the contravariant one. The covariant one instead is E over C minus Px minus Py minus Pz. So the 4 vectors that have 3 minus 1 are the covariant one in the notation we have written. And so, for example, if you have P mu 1, P mu 2, of a particle 1 and a particle 2, this object is E1 over C, E2 over C. Then one is within the index up, and the other one is with the minus, and the other is with the plus. So you get P1 times P2. These are the 3 vectors. Now, if you do, for example, x times P, this is x mu, P mu. Then remember x as a CT, and P mu as E over C, just to keep the dimension. This one now has the dimension of a length, and this one, E over C, has the dimension of a momentum. If you do this, the first component, the C cancel, and you get ET minus x times P. This is, when I put an arrow, it means that for the 3 vectors, okay? Now, the 4 quantity that we will define is the following. We will define a momentum with index up, defined in this manner. Now, this object with the index down is the covariant. So why did I put, so this is a definition. It's a definition of a differential operator in this manner. Do this as a homework. So I write here homework. This has the index down, so x mu is covariant. And you know it transforms. Prove that P mu is contravariant. Keep in mind the dates in which you have to give me the homework, okay? This one belongs to the one that you have to give on at the end of July, 26th of July. So up to now, the homework I have given to you, you have to submit by the 21st, okay? So this is a definition, 21st of June. So this belongs to the other set. X mu has the index down, so we know that this x mu with the index down transform as a covariant vector. This one, I want that you prove, you see it has the index down, that it transforms as a contravariant vector. That means with the normal lambda matrices, okay, with this definition. Now let's see what we get from this P mu, EH, dx mu, and then basically it is IH derivative. Now let's go and see x mu with the index down, what it is. It was this object. So basically we get derivative with respect to CT, then we get minus IH derivative with respect to x, minus IH derivative with respect to y, minus IH derivative with respect to z. So you see that the covariant one has the space part as you knew. Okay, this is often written also AH derivative with respect to Ct minus the gradient of this. Now let's see P mu. Remember, I bring the index down and I have just to change these signs, and what you get is h minus h squared d dx mu d dx mu. This one with the index down correspond to this. This one with the index down correspond with the x mu with the index up. It's not just a game. Really, this object transforming x mu as a covariant vector imply that this one transform as a vector. And the reason is this is in the denominator. When you bring up not the inverse of the matrix, but the direct matrix. And the same with this one. Now, if you do this, remember, one has index up, the other has index down, so the sign here change, and what you get is the following things. Minus h squared. The minus h squared come because I have IH, and I have minus h squared. Then I have 1 over c squared, the derivative with respect to t squared, and then I have d dx squared minus d dy squared minus d dz squared. Okay, so this is basically minus h squared 1 over c squared d dt squared minus the Laplacian. Okay, this object sometimes is also called with these 4 Laplacian, these box things. Now these are all boring convention. You have just to get accustomed to it, playing with it, because in half an hour you cannot really grasp the thing, so you have to work it at home, the detail. Now, so that we have all these set up, let me see if I have something else to tell. No. Now let's start relativistic quantum mechanics. Relativistic quantum mechanics, it means we combine quantum mechanics with special relativity. Please. I cannot hear, I'm deaf. Really, I am deaf.
Previously, we defined momentum as dx by d tau is a proper tau.
Right, but that is a C number. This is an operator.
So,
I mean, this is a definition of operator. It has nothing to do with the P mu that we define dx d tau. This is a C number, is a number. Okay, this is an operator, so I define this operator. If you don't want to call P, you can call in another manner. If it confuses you, that is related to that, okay? But this is an operator, and this is a definition, so you have just to take it. From now on, every time you see a hat on a P mu, it means this.
so momentum, how does it transform? Because
Oh, this object with the index down under the Lorentz, it transforms as a contravariant vector. So that means directly with the lambda, not with the inverse of the lambda. Okay? Now, if you diagonalize this, it's possible to prove that if you diagonalize this, you get this object as eigenvalues. Okay? Now, few important things about combining quantum mechanics with relativity is, so basically we combine quantum mechanics plus special relativity, and we get relativistic quantum mechanics. And this is the subject that we will go on till the end of the course, writing down the analog of the Schrödinger equation, and so on. Now, which are the 4 important ingredients? Well, in special relativity, time and space are combined. When you do a Lorentz transformation, you see that delta x change in a manner that pull in delta t are combined. So basically we can only talk about space-time. We cannot talk about space and time. No, time gets transformed, and how it gets transformed, it injects into a transformation of time delta x, vice versa. A transformation in delta x you remember, delta x prime is delta x minus d over c squared delta t 1 over d squared c squared, and delta t prime is delta t minus vc delta x. Maybe I did something wrong, but just to tell, delta x pulls in delta t, and delta t pulls in delta x, so it's not anymore x and t invariant, but it's space-time that is combined, and what is invariant is the 4 length, that is c delta t square minus delta x square minus delta y square. So this is the first ingredient. Second, so this is special relativity. This is the main message of special relativity. Which is the main message of quantum mechanics? Well, the main message of quantum mechanics is delta x, the uncertainty principle. So the best that you can localize an object is this. We know that the uncertainty principle is bigger than this, but let's say if we do the best things, we can localize an object. If the uncertainty in P is of this form, then has this value, then the best you can do is to localize it. The smallest distance into which you can localize an object is this. That is the smallest one. Okay. Now, I will now show to you. We want to describe. We would like to describe relativistic quantum mechanics of single particle. Now, out of these two, I will derive that actually, you know, in non-relativistic classical mechanics, you can have delta P as you like. That means it can be very big or it can be very small. Here, if I put into these things, the delta P, the maximum delta P that I can get is this one. Why? The maximum delta P, so this is the uncertainty in delta P. If I want to describe single particle, this is the maximum uncertainty in delta P I can have. Why? Let's remember the famous relation P squared minus P squared C squared equal MC squared 4. The famous, that E and P are related by this. Okay? Then if the momentum is this object, you get E squared minus the momentum is this object, so you get M squared C squared equal M squared C4 squared, but this means M squared is 2 M0 squared C squared, and this describes two particles, right? Two particles at rest. So if I cannot go beyond this, because if I go beyond this, I have to stay always less than this quantity, because otherwise I describe two particles. This is the energy of two particles, because it's two, this is just, I consider only the mass energy. So the relativistic things with this extra ingredient tells me, listen, delta P cannot be bigger than that, but then delta X at most can be this. But this, what is this? This is something that you know is the Compton wavelength. So a single free particle cannot be confined to a distance that is less than the Compton free length. If you try to go beyond, that means to localize at a closer distance, then the denominator increases. If the denominator increases, it means you are not describing a single particle, you are describing more than one particle. Here what is happening somehow is that you have pair creation. Okay, so I repeat the step because usually it is just stated and not derived. This is not a rigorous derivation, but something that makes you understand. This is the uncertainty principle. There should be a bigger, but let's say this is the smallest distance in which you can localize a particle in non-relativistic quantum mechanics if the uncertainty in P is delta P. Now I'm saying, listen, in relativistic mechanics, quantum mechanics of a single particle, the highest uncertainty you can have is of this form. Why? Takes this relation, okay, and let put in this value. If you put in this value for P, okay, remember that this, you can put in this value for P in the sense that you have some momentum and then we increase that momentum of this amount because there is a delta P. So neglecting the previous part of the momentum, let's insert the extra part that is this. Then if we get this, bring on the other side, and you get the total energy is the total mass energy of two particles. Then we are not describing anymore the single particle. So putting a minus, it means we are these things. So we are describing one particle plus a lot of kinetic energy, but not two particles. If instead here we say bigger than that, then it means bigger. So if delta P, like in relativistic, in non-relativistic classic quantum mechanics, could be anything, in quantum mechanics is not so, because if it were anything like bigger than that, then you would have that E is bigger than this. That means it describes more than one particle, while we want to describe single particle. Okay, so it means this is less than that, and this is less or equal. Less than that, then it's less than that. That means we are describing one particle because this is less than 2. So one particle, m0 c squared, plus a lot of kinetic energy. But a lot of kinetic energy that is not equal to a mass, so it cannot create another particle. If there is this bound on delta P, so this is a bound on delta P, on the uncertainty of P, if you want to describe a single particle in the relativistic regime. Then if there is a bound, that means this must be less than that, less or equal, let's say, then delta X at most can be this quantity, and this is the Compton wavelength. It means at most, if you don't want to create other particles, you can localize a single particle into a Compton wavelength. Now, why you cannot go beyond? What is happening? When you want to go beyond, you have to increase the energy. Okay, if you want to probe shorter and shorter distance, you have to increase the energy. Then what happens is that that energy is enough to produce two particles, so you are not describing anymore a single particle. Okay, so you had one particle you were describing. Now, this one, we know that we can localize inside a distance that is at most the Compton wavelength. If now we try to localize at a smaller distance, so inside of, we need higher and higher energy. Then if we go to higher and higher energy, we could go beyond the 2m, that means create pair of particles. So if you try to localize in a smaller distance, the energy is such that it will create pair of particles, because charge has to be conserved. So if this was zero charge, also what you create is bigger than that. So combining spatial relativity with quantum mechanics put a bound on delta P, and it put a bound on so all this is, is never specified enough. All this is if you want to describe single particle, and we will see there are troubles. There are troubles. Yes, please.
So in this case, the Compton Is it the smallest distance you can localize a particle, or?
Yes, it's the smallest distance in which you can localize the particle if you want to stay with single particle. That means, for example, at CERN, at LHC, and so on, they go at much shorter distance than the Compton wavelength. They can localize the electron at a shorter distance than the Compton wavelength. But what happened? That they need so much energy that they don't localize only the electron. They get around all a cloud of other particles. So then this is not anymore the theory of a single particle. So if you don't want to create other particles, at most you can localize a particle in a distance of its Compton wavelength. You can go beyond, but the price you pay is that you create other particles. So this is the crucial ingredient that is never stressed enough in papers, okay?
Question.
Please.
We are talking here about just one mass, one body of mass.
Yes.
So if we create a particle, it necessarily will be with the same mass as the previous one?
Well, if you, yeah, well, that is a sort of an approximation that I did, okay? You can say, your question is, oh, maybe I can create another particle with a mass that is less and then everything goes through. But what happens is the following. In principle, that reasoning is okay. But if you have only one particle, you have only, that means, let me put in another manner because it's a little bit tricky. When we started, we had one particle, so we had only that kind of particle, we had only that kind of mass. If I have only that kind of mass, of course I can create particles with lower mass, but the only reference number I have is the mass of this particle, okay? In principle, you could, your things is right, you could create particles with less mass and then stay into that limit, but it still is not a single particle description anymore. Even if the one that you created have a smaller mass, still it is not a single particle description. Okay, so that is the main concept I wanted. If you want to stay with a single particle description, then at most you can localize into that things, or you know, it is of the order. When I put of the order, it means, well, yes, if you create a particle with less mass, then you could go maybe a little bit lower, but still it is not a single particle description anymore, okay? So now the other points that are important, so here, yeah, another thing that is important, another thing that is important is as time and space are combined, then if I have an uncertainty in X, I have for sure, doing a proper Lorentz transformation, an uncertainty in T. And we know that C delta T as dimension is delta X. Now this we know is H over M0C. So we get that there is an uncertainty also in time that is H bar M0C squared. Because space and time are equivalent in special relativity. I can turn one into another. Then if there is an uncertainty, a minimum uncertainty in X, that means you cannot probe distances at the, you cannot probe particle at a distance less than this one, then this delta X is something like C delta T, then there is an uncertainty also in T, and that is the things. This means that when I give something like wave function X, Y, Z, T, I have to be careful because this is not, it cannot be a number. We know that there is a minimum uncertainty that is this, so this object starts losing its meaning, and also the probability density start losing its meaning. So we have to be careful and see what it means. We will use, but we have to be careful that t, a precise instant of time, and also precise x, has not really well defined meaning in this framework. That means there is a minimum distance and a minimum length if you want to describe single particle. If you don't care describing single particle, you can probe and have further things. Okay. Now, before I said to your friend that asked me before that P mu is defined as dx mu. Then immediately from here we get which are the commutation relation between this strange object. Now they all become operator, and if this is the definition, this object is defined in that manner. Forget its relation with momentum. It's an object defined in that manner, and I know the space part is the usual momentum that you knew. From here I can say IH d dx mu. This one I have to write because you know it has an index up. Let me see. Yeah. No, wait. This one I get. Let's see the result of this. Let's do in the following manner. And then I do G nu sigma x sigma for this. This object is H G nu sigma dx sigma dx mu, and this is I G I H bar G nu sigma, and I have to divide this by this. There is something I did wrong here. Yeah. Now, you see this object that is down, look, you can say, how do you define an object that is down with an object that is up? But this object with the index down, as it is derived, is, sorry, yes, please.
X is correct, right, when you define the momentum operator?
I define in this manner
With X in the...
down. Down. It is down here. And it is down here. Then it is down here. Now I define this is nothing else than delta sigma mu, delta sigma mu. So this one is nothing else than EH. Let me see if I am doing things right. Delta sigma mu, so I get E, G, H, G, mu, mu. Okay, so this commutation relation is nothing else than E, H, G, mu, mu, or nu, mu, but it's symmetric. If you remember the form of the G, mu, nu is symmetric. Okay, so these are the commutation relation. Now, okay. Well, as you are doing quantum mechanics, we want, like in the non-relativistic case, to have an equation of motion, the concept of wave function, and all this. You don't need to take note because I'm really following step by step this book. So if you have this book. Now, let's see how we can derive the relativistic. Or we can derive an equation of motion, now that we have defined these things. Let's start in the non-relativistic case. In the non-relativistic case, the Schrödinger equation was d psi dt, the time-dependent 1 minus h squared 2m plus v of x, that is the potential psi x of t. And we know that this somehow is the same as the energy operator is equal to the momentum to m plus v of x, okay? And we realize this as IH ddt and so on. So this equation, that is the Schrödinger equation, gives as energy momentum relation this relation. But this is not the relation that we have in the relativistic case. Okay, let's take for the moment, to be simple, in the non-interacting case, so let's take away the potential, The Schrödinger equation basically is an implementation at the operatorial level of this relation. This is not the case, this is not the relation we have in the the momentum case. In the relativistic case, if you remember, the relation was the following: E square C square minus P square equal M0 square C square. This was this mass energy relation. So if we turn this into an operator relation, in analogy with what you know is not a derivation of the Schrödinger equation, but from this you say, well, let's introduce an energy operator and a momentum operator, and let's impose this relation. Now we have this mass energy relation, at least we can do that for the free particle and for the free waves. For the free waves, okay, if this is interpreted as IH ddt and this is interpreted as IH ddx and so on, then everything works. So, but this is not the relation that we have at the relativistic level. At the relativistic level, we have this, that operatorially we could say this is nothing else than P mu equal M0 square C square. Okay. Now that means, you know, in quantum mechanics, from this relation you postulated this, then it is equivalent to this equation. And you postulated this because you did the operator analog of the relation between energy and momentum. Let's do the same here. That means this is the energy-momentum relation. Let's postulate that at the operatorial level there is this relation. Then if there is this relation with the P mu that we have defined, remember that P mu was defined as IH dx mu. Then from here we immediately derive the, okay, if this is an operator relation that we have postulated, we can apply a wave function. But now let's insert this expression, and what we get is the following things. 1 over c square, the second derivative with respect to t square, because here there is a c, okay, so it's c. There is a second 2 times the derivative with respect to t, then minus d dx square minus d dy square minus d dz square. This is this part. It is applied on a psi, but also this is applied to a psi. So now I have to be careful with the sign. If I bring the other things on the other side, I have to be careful here because there was a minus h bar. Here there was a minus h bar that I forgot. That minus h bar I bring down, and I bring it in the denominator, and I bring this on the other side. So the net result is mc square h square psi equals 0. Now, let's be careful. It means this relation is equivalent to this operatorial relation if I interpret E as I h bar ddt, if I interpret this as I h bar d dx and so on and so forth. So why we did that? We basically turned this classical mechanics relation into an operatorial relation. Then we applied psi and we got this equation. Okay, we applied psi on the left and on the right hand side and we got this relation. Let's do the same at the relativistic level. So this is non-relativistic. Now let's do relativistic. This is the normal relation in classical relativistic mechanics. Let's promote everything to be operators. Then we get this relation. That one is equivalent to this relation because P0 is nothing else than E over C. Then this is an operator relation. Here there is the identity, if you wanted, the operatorial level. Let's apply the wave function as our operators to both sides, and we get this. And this, when you write P mu in this manner, is this equation. Okay, you see, this is a new equation, is the analog of this, but only analog because you see, here there is no C. Here instead there is C. Here there is no second derivative, only first derivative. Here there is second derivative. This equation is called Klein-Gordon equation from the name of the two physicists that first wrote it down. And they wrote it down just after 1 year or two after the Schrödinger equation, just because, you know, special relativity was around since 1905, so it was easy to write it. But there is no potential, so this is Klein-Gordon equation for the free particle. And of course, it's a wave equation. Now, let's see if this equation can be, is the free case. You know, in the free case of the non-relativistic, which are the solution. The solution are the free waves. Okay, so let's see if this one has solutions that are analog of the free waves. So now let's stick to this. Let's see if it has a solution, free waves. So it means now we have got this equation. This is the free Klein-Gordon. Let's look for some solution. I can prove to you that, and I will do, that this solution defined in the following manner: minus IH P mu X mu, that means is exponential minus IH P0 X0 minus P times X. And this is exponential IH bar P times X minus E times T. You see, there is no C bar. I will prove to you that this is a solution of that, provided P and E stay on the mass shell, satisfy the famous relativistic relation. Okay? So now I want to prove solutions. I want to prove that this is a solution of that free equation. It's very simple to do it. Okay? Just insert these things there, and what you get is you have to do derivative with respect to t, so you get e squared over c squared. So let's apply this to this. Here I have derivative with respect to t 2 times. I have e, I have IH, but let's forget for the moment IH, and as divided by c squared. Then I have I have derivative with respect to x, and it provides me, again, I neglect about these things, but actually let's put it 2 times. You understand? 2 times the derivative, it brings me down e, IH 2 times, then I have a minus because I bring it down 2 times. Then I apply this on this, and I get P vector 2 times, right, sorry, and of course then I get 1 over h square, and then I have 1 plus mc square h square, that is the last term, multiplied by exponential I over h px minus et equals 0. So, is this a solution? So I have applied this solution, inserted in here, do the derivative, and I get this relation. Well, this object is not 0. So this object is 0 only if this is 0, but this is 0, it means the following. Okay? So they are solution only if this quantity is 0, but it means it is 0 only when we are on the mass shell relation, when EMP entering here satisfy this relation. Okay? If you do the analog for the Schrödinger equation, what did you get? If you do the analog for the Schrödinger equation, you find that these free waves are solution only if E is equal to P square over 2M. Okay? So these kind of free waves are solution if the parameter that enter P and D satisfy some constraint. In the relativistic case, the constraint is this. In the relativistic case, the constraint is this, that this must be 0, that is equivalent to this. Okay? So this is the Klein-Gordon for free case, and they have a solution free waves of that form only if P and D satisfy that relation. It is the usual mass shell relation. Next time we will go on and see that there are, to analyze a little bit better this relation and see what happened, okay? I don't have to send you any notes because basically I am, if you are following this book, basically we reach page 5, not even completed page 5, okay? And, okay.